From a collection of Unmitigated Pedantry, the blog of history professor Bret Devereaux. Archery, distance, and kiting. This week, we're going to look at how the effectiveness of arrow fire, especially against armored targets, varies over distance. This is, in a sense, a continuation of my previous post on armor penetration, punching through some armor myths, so you may want to refer back occasionally. This is going to be a longer post with a bunch of math. I think the math is very interesting, but I understand some people don't. On the flip side, I know if I leave it out, some folks will be very confused as to how I got where I was going. If you just want to contrast how things are shown with how they probably were, read the first two sections, then skip down to quick sum up, and pick up from there. My target today, excuse the pun, is less portrayals of pre-gunpowder warfare in film or TV, and more how it is portrayed in interactive media, like tabletop war games and video games. It thus has less to do with how everything looks, and more with game mechanics. So let's start there. Mechanics, and the problem. Games that attempt instead to simulate the complex effects of wounds, Dwarf Fortress, RimWorld, are very rare. In most games, the effect of weapons is reduced to a mathematical abstract, damage. This weapon does 5 damage, that weapon does 10, this enemy has 25 hit points, so you must hit him so many times, that sort of thing. I broadly understand the necessity of that abstraction, and I am not going to complain about it here. We can understand the damage statistic as a simplified measure of lethality well enough. Image: Xingqiang with army. Image description: some archers, along with Xingqiang, being her badass self. End of image description. Instead, I want to focus on the way ranged weapons, especially arrows, are handled within these sorts of systems. Let's take the example of the Total War games. In this case, Total War: Three Kingdoms, because I have been playing a bunch of it. These basic archers have a range of 200 and an arrow damage of 53, 31 regular, and 22 armor-piercing damage. What that means in the game is that these guys can only fire at enemies under 200 units. I think it's in meters, but it is really hard to tell. When each model, each guy, fires, the game calculates a trajectory for his arrow. If it intercepts another model, friend, or foe, it deals the 53 damage listed. It doesn't matter if the target is 199 meters away or 2 meters away. It deals 53 damage. Against armored targets who can resist some of the damage, the arrow does 22 guaranteed damage, the armor-piercing value, and the 31 regular damage is reduced by the armor via a complicated formula. Rather than tracking probability of a sudden lethal hit, the target is killed when the cumulative damage from the arrow hits exceeds his hit points. Range is still not a factor in damage. Now that's not to say greater ranges do nothing in-game. The arrows have scatter to them, each shot is a little bit off. The longer the range, the more time for the arrows to spread out on their individual trajectories and create the chance of missing. Amusingly, a shot that, by accident, goes long still deals full damage. You can see this clearly with artillery. But you can only shoot that far by mistake, never on purpose. The upshot of this is that the range of the ranged weapons is a hard limit. Inside, full damage. Outside, no damage. You see the same effect in RPGs like Divinity: Original Sin or Pillars of Eternity, where ranged weapons either do full damage or no damage. It's not an uncommon system at all. But we shall not discuss the cringe of systems where the damage stat belongs to the arrow instead of the bow. But I want to stay focused on Total War for a second because of how it influences the tactics in the game, and thus the common perception of historical tactics. So, what effect does this simplified model of ranged combat have on the tactics of archery? First, small differences in range become very important. The difference between a range of, say, 180 and 160, for example, the difference between High Elven archers and Empire crossbowmen in Total War Warhammer 2, seems trivial, but is actually very significant, because at a range of 180 or 170 units, the former group deals full damage and the latter deals none. Second, tactics that involve skirmishing with fast, long-range units, like horse archers, happen at the very limit of their effective engagement range. That is, horse archers with a range of 200 are going to sit at 200 and fire, moving away so as to maintain that huge range. That makes differences in speed important too. If those horse archers were close, a slower unit, like another kind of cavalry, might be able to surprise them with a sudden dash, but at maximum range the chance of that happening is basically nil. The only way to bring those horse archers into a fight is to use a faster unit. And in games where there often are no faster units, the only response to horse archers are either foot archers with equal range or simply enduring the long-range fire. Of course, that further enforces the supremacy of maximum range. Bringing inferior range 150 foot archers does literally nothing to protect an army against range 200 horse archers, since the latter will never let the former in range to even shoot, despite the fact that this very thing was an effective way to at least mitigate the impact of superior enemy archer cavalry historically. Image: relief of mounted Assyrian archers. Image description: pictured, Assyrian mounted archers. Note how they are not firing at a standstill, but charging the targets they are shooting at. End of image description. Why do I care? Because these games are the only experience with tactics, let alone pre-modern tactics, that most people will ever have, and I see these implications seeping into the way my students think about these weapon systems. Students also, without realizing it, bake these assumptions into papers, obsessing about maximum range and movement speed, often over other more important considerations, like morale and battlefield psychology. So let's drop the game mechanics and start thinking about real-world mechanics. Range and power. Thinking in probabilities. The first thing we need to note is that, at least in Europe, the Middle East, and the Mediterranean, by late antiquity, and I would argue earlier, most soldiers on a battlefield would wear at least some armor. That might mean only a textile defense, or it might mean more significant metal defenses, but there is typically something an arrow or crossbow bolt must defeat in order to score a lethal hit. Last time, when we discussed penetrating armor, we did so mostly in binaries. Can weapon X, under ideal conditions, defeat armor Y? And that is generally how penetration tests are done, under ideal conditions. The armor being tested is unmoving and secured so that it takes the full force of the hit. The one notable exception was a set of tests Mark Stretton did, where the armor was moved towards him at charging speed, making it easier to penetrate, to simulate firing into a cavalry charge. It is struck by someone who can concentrate fully on delivering the heaviest blow possible. If a ranged weapon is used, it is fired at point-blank range. The hits that count are strong blows delivered dead on. But in battle, we're not dealing with one arrow, but hundreds, and thus not with a binary, penetrate or not penetrate, but a range of possibilities, impossible, unlikely, maybe, likely, etc., influenced by a host of factors. The most obvious of these is accuracy. Some percentage of shots will miss, and thus fail to inflict casualties regardless of the energy of impact. At the same time, Some percentages of shots may strike unarmored or vulnerable areas, face, neck, eye slits and visors, etc., and kill even at very low energy. Thus, at almost any range within bowshot, there is at least some chance that any shot will be lethal, disabling, or miss entirely. The closer the enemy gets, the more accurate the volley becomes, and thus the higher lethality goes. We should understand defeating armor as a probability cloud in the same way. And remember, nearly everyone is at least wearing some basic textile armor. Most quite a bit more. The main factor here on the attacker's side is the energy of impact and the shape of the arrowhead. High energy of impact and a properly shaped arrow, read Bodkin, increases the chance to penetrate. At point blank range, the energy of impact depends on the draw weight and the draw distance, because the longer the power stroke of the arrow, the more time it has to be accelerated by the string. But the bows of a group of archers will not be perfectly uniform. The war bows recovered from the wreck of the Mary Rose, when reconstructed, had draw weights running from roughly 100 pounds to roughly 170 pounds, and may have been pulled to slightly different draws. Strickland and Hardy, The Great War Bow, 2005. That in turn means that even within a single volley, the arrows will arrive at a fairly wide range of speeds and impact energies, further compounded by handcrafted arrows of slightly different weights and dimensions. Different types of arrows will have even more variance. How does range influence those probabilities? Power over range. Let's start by recalling some of our energy thresholds for penetrating armor under ideal conditions. 50 joules of impact energy behind a spear point was sufficient to defeat a 16-layer, quite thick linen gambeson. An arrow might need somewhat less. Williams's mail failed around 100 joules, but we ought to construct a broad range here. The mail he used was of fairly high quality, and he used a lot of padding behind it. We might suppose mail would fail at energies between 60 to 100 joules, which seems to fit with other tests I've seen. Plate armor, which we might extrapolate also to lamellar and brigandines, have a range of failure energies based on metal quality and thickness, from 1 mm soft iron plates failing at as little as roughly 30 joules, to 2 mm steel plates withstanding 180 joules. We can visualize this in a chart of the energies required to have a chance of defeating armor. Note that to actually kill the person, a hit needs to significantly exceed these energies, perhaps by 10 to 30 joules. Image. Range chart of the impact energy to defeat armors with arrows. Image description. The blue-red bars represent the energy zones where penetration is possible but not assured, depending on armor quality, etc. Caveats. This follows Williams 2003. Iron here corresponds to Williams 2003's armor 0% carbon, 3 to 4% slag. Steel to his armor 0.6% carbon, less than 1% slag. Remember that armor comes in layers. Mail is being worn over a gambeson, not alone, usually. End of image description. Estimates for the firing energy of the most powerful bows vary significantly. Most of the research that I am aware of has been done on English longbows, but I want to note that the draw weight and draw length of steppe composite bows, for example, Hun, Turk, Mongol bows, are quite similar, giving them similar, as I understand it, range and power characteristics. Many bows were not this strong. These are some of the most powerful bows out there. I'm going to give some of the estimates here in a quote box so that folks who don't want to stop for them can skip over. Boring data box. E. McEwen, Experimental Archery in Antiquity, 1988, used an 80-pound U bow to fire a 50-gram arrow at 53 meters per second, 70 joules, and a 90-gram arrow at 43 meters per second, 83 joules. He also measured a modern 100-gram crossbow bolt fired from a crossbow with 90 pounds at 62 meters per second, 192 joules. These are the figures Williams, 2003, uses. Mark Stretton in H. Soar et al., Secrets of the English War Bow, 2006, has done testing on Italian U-bows with a range of energies between 90 joules and 114 joules, with a 140-pound bow with a 32-inch draw. Energies depended on arrow type and weight. Todd's Workshop tested on their crossbows with a 1,000-pound draw firing a 90-gram bolt at 47.9 meters per second, 110 joules. Magyar, Nowak, Tomaz, and Zukowski, Numerical Analysis of English Bows, 2017, available online here, attempted a simulation test with a maximum energy on the arrow at 25 meters of 130 joules for a 150-pound bow. They used a very heavy 96-gram arrow, which launched at a speed of 53 meters per second, launch energy of 134 joules. Given the divergence between their results and practical tests suggests something has gone wrong. I suspect the launch energy is too high. See, for example, Stretton above. Mike Lodes, The Longbow, 2013, notes a test fire by Mark Stretton with a launch speed of 170 feet per second, 51.8 meters per second, but does not give the arrow weight. Very recently, Justin Ma and Blake Cole filmed a test of a 113-pound recurve bow with a 28-inch draw, which, depending on arrow weight, had a launch energy of roughly 110 joules. This is, by no means, intended as an exhaustive list. Compared to our chart, those are some formidable numbers indeed. Many of these bows' launch energy exceeds the ability of mail or even plate armor by quite a bit. But what does range do to them? A lot, it turns out. Lodes, original citation, notes that a test shot from a 150-pound bow decelerated from 170 feet per second, 51.8 meters per second, to just 137 feet per second, 41.75 meters per second, after just 0.8 seconds in flight, though this was on the ascent. Magyar et al.'s model suggests that, accounting for speed picked up in the descent, a heavy bodkin arrow might lose roughly 6% of its speed fired at 100 meters, and 10% at 200 meters. Though, as noted, something seems a bit off about Magyar et al.'s simulation. Lodes notes quite correctly that the deceleration for a crossbow is much worse. Crossbow bolts have to be thicker than arrows to withstand the forces they're subjected to. Crossbows have much shorter draw lengths than traditional bows, so the bolt has less time to accelerate, which means you need to put much more force on it. Which is why crossbows with massive poundage often fling bolts not so much faster than longbows. But that means, leaving the crossbow, the bolt is thicker, less aerodynamic, and moving faster, so more wind resistance, meaning that its velocity drops off even faster. This, if you are curious, is how crossbows manage to be both more powerful and shorter ranged than traditional bows. Since the kinetic energy measured in joules of an object equals 1/2 mass times the velocity squared, a drop-off in the speed of the arrow actually has a larger effect on kinetic energy. Taking Lode's example and assuming a heavy 90-gram war arrow, the energy at launch was 120 joules, but after just 0.8 seconds in flight, that would drop to just 78.5 joules, a 1/3 drop in kinetic energy for just a 19% decline in speed. Admittedly, this doesn't account for the arrow accelerating again as it descends on the back of the parabolic arc, following Magyar et al.'s experiment, suggests an arrow might lose roughly 10% of its energy if it impacts at 100 meters, and roughly 20% at 200 meters. Of course, this will depend on all sorts of other variables: wind, arrow shape, weight, etc. But it provides a decent rule of thumb to make the point. But wait, it gets worse. Because angle of attack. So far, we've been assuming a dead-on hit from an arrow, but dead-on hits would have been fantastically rare for a variety of reasons. First, rigid armors, plate, brigandine, etc., were shaped to deny flat surfaces to an attack, making dead-on hits improbable even at extreme close range. But range also plays a role in altering the angle of impact, even against a flat surface. As the range of an arrow shot increases, so does the angle of impact. The reason, of course, is that the arrow has been shot up into the air and is now descending at an angle. Armor provides very few surfaces angled so that a descending object will catch them perpendicularly, if for no other reason than that most humans are taller than they are wide, and so most armor surfaces are nearly vertical. The exceptions, like the crowns of helmets, tend to be thickly armored. The angle of descent is essentially a product of how close the shot is to maximum range, generally achieved by a roughly 45-degree shot. Because of air resistance, shots always strike with a somewhat more severe angle of impact than they are fired with. Note that I am measuring the angles from the perpendicular, so a dead-on perpendicular shot would be 0 degrees, whereas an arrow coming straight down would be 90 degrees. This isn't the clearest system, but it is how Williams 2003 measures the angles, so it is the easiest for me to use here. High angles of impact are very bad for arrow penetration for two reasons. The first problem is that much of the energy of motion is along the target rather than into it, meaning the arrow might glance off rather than penetrate. Even if the arrow bites into the armor, some of the energy will be lost pushing down on the armor rather than pushing through it. But the second problem is that a hit at an angle has to move through more material than a dead-on strike, making the armor effectively thicker, much like sloped armor on a tank. The effect of these factors on penetration is severe. Here I am giving only a fairly simplified version of the effects of sloped armor. The question has been examined in far greater detail in reference to high-velocity rounds striking tanks. Williams 2003 looks at the problem of glancing. He estimates that the energy to defeat a steel plate at a 30-degree angle is at least 20% higher than a dead-on hit. A 45-degree angle is 40% higher, due to the arrow not delivering its full energy to the plate. A 60-degree impact requires double the energy to penetrate. This may be less true of armor made from materials the arrow can bite into, like mail and textile, but some of the energy of impact will be lost regardless. But Williams here seems to have only considered the arrow's side of the equation, the energy lost to the fact that the arrow isn't moving perpendicularly to the armor. The arrow also has to move through more material, metal or textile, because the armor is effectively sloped relative to the projectile. This increases effective thickness. At 30 degrees, the increase is 16%. At 45 degrees, it is 42%. At 50 degrees, it is 56%. The benefit to increasing thickness is not linear, but actually exponential, roughly to the power of 1.6. So these increases in effective thickness can have huge impacts. The difference between a 1 millimeter plate and a roughly 1.4 millimeter plate, effectively a 45-degree angle of impact, is not 40% more, but 75% more. Image: chart of the angles of attack and armor thickness. Image description: chart of both the angles I am describing and how the angle of impact affects the amount of material the arrow must push through to defeat the armor. End of image description. Determining the impact of these factors on mail and textile, complex materials compared to a steel plate, would probably require a lot of real-world testing. On the one hand, the arrow can bite into the ring or weave of the fabric of these armors. On the other hand, these materials have vertical give, which may well absorb much of the arrow's energy, as the arrow must push the armor down before it can apply full force to splitting the rings or breaking fibers to push through. For mail especially, the arrow's tip needs to find the center of a ring to split it, which becomes far less likely at impact angles further away from the perpendicular. Quick sum up. Penetration at range. With all of that information in hand, we can, very roughly, think about armor penetration over range. I want to stress that this is all back of the envelope guesstimation. The studies don't really exist to be precise yet, since there are so many variables, release energy, release velocity, arrow weight, arrow drag, etc., involved. But we can still get a sense of the issue. Let's take 3 bows, the absolute strongest longbows tested. 140-pound draw, 120 joules release energy. For example, the Stretton tests. Then, we can also consider a more typical longbow, with a roughly 80 joules release energy consistent with the 120-pound pull average Mary Rose bow. Finally, a 60 joule release energy benchmark, so we can see what happens with a bow that is generally inferior to the English longbow, or perhaps an uncommonly weak English longbow archer. In all cases, we're assuming an appropriate bodkin point. I'm going to use the phrase effective impact energy to refer to my guesstimate of the energy delivered after both speed loss and angle of impact are taken into account. This is not a scientific term and should not be treated as such. When you read this, be thinking that a given mass of archers is likely to have bows with power spread out in this range. So again, we're dealing with a probability cloud, not a strict binary. At short range, 20 meters or so, all of our bows have nearly their full impact energy, and the angle of impact is very low, around 2 degrees, negligible. At this range, the most powerful longbow is very likely to defeat everything short of a 1.5 millimeter steel plate with padding. Thinner plate defenses are likely to be damaged by the impact, even if they are not defeated. The more typical longbow has a good chance of defeating mail with a well-aimed shot that strikes square on and might damage plate defenses. The weakest bow will struggle to defeat but may damage mail at this range. Our combined close-range volley is very dangerous to anyone who isn't wearing well-made and thick plate armor. At medium range, 100 meters, things are a bit different. Our arrows have lost some energy, we'll say roughly 10%, but because wind resistance is higher the faster you go, the energy loss will be most extreme for the heaviest bow. And their angle of impact is less favorable, roughly 10 degrees or so, assuming our bows could throw an arrow around 250 meters. So figure 10% more defense material to get through due to effective sloping. For our most powerful bow, effective impact energy is right around 100 joules at this range. Mail penetration is no longer assured, but still quite possible. For our typical longbow, effective impact energy now roughly 65 joules. Defeating mail will require some luck, but simple gambesons should still be defeated frequently. For our weakest bow, effective impact energy now roughly 50 to 55 joules. Defeating a good, thick gambeson is a solid maybe. Everything else is solidly out of reach. At this range, well-armored foot soldiers, wearing something like a brigandine over mail, for instance, can advance with some confidence, More poorly armored soldiers, however, are still very much at risk. At long range, 200 meters, things get much worse for our archers. Our arrows have lost more energy. We're up to roughly 20% total loss, and the angle of impact is now much less favorable, close to 30 degrees. The natural sloping effect of our angle of impact now also means we have to get through 16% more material. For our most powerful bow, effective impact energy now only around 80 joules. A mailed enemy is not free from fear, but many of our arrows will strike and fail to penetrate. Even a thin 1mm steel plate is sufficient for total safety. If you're wondering, wait, why isn't it as good as the typical longbow was at close range? Angle of impact. There's more mail to get through. For our more typical longbow, effective impact energy now around 55 joules or so. We'll really only defeat textile armors, and even then, only some of the time. Our weakest bow, impact energy now roughly 40 joules, will likely fail to penetrate even a good gambeson on a solid hit. If the bow can even put an arrow out this far, at this range, enemies in mail can consider themselves quite safe. Plate armored foes are effectively immune to our fire. Of course, other things are happening as the range extends. Accuracy is decreasing as well. At 200 meters, our best bow's arrows have been in the air for around 4.5 seconds. Of course, at this range, we're shooting at masses of men, not individuals. I should also note that at extreme ranges, the arrows are in a sharp descent, which makes them far more likely to hit the pauldrons, shoulder armor, or the crowns of helmets, some of the thickest and most effectively sloped parts of the armor. I should also note that I have, in part, understated the problem of impact angle because of the way armor was shaped. We've assumed there's only one angle in play, the angle of the vertical. But in fact, the armor is shaped in a three-dimensional space, meaning that in addition to the slope introduced by the arrow's descent and the vertical slope of the armor, it may also be sloped horizontally. Think about striking a globular breastplate an inch to the right of the center line. The arrow will glance off to the right as well as downward. That means our impact angles are, in most cases, effectively minimums. The actual angle of impact, in many cases, will be less favorable for penetration. The key takeaway: the lethality drop-off for bows against armored enemies at range is fairly severe. It is, I should add, even more severe for crossbows, which, as noted, decelerate much faster once fired. Alas, more testing is required to figure out exactly how fast. Thinking about a longbow volley, if we imagine a bell curve of release energies centered around roughly 80 to 90 joules against an armored advance, we can figure that at 200 meters, only the strongest bows will have good lethality against armored men, even if just mail or a gambeson. The amount of threat that the bows can throw out to their maximum range is actually almost negligible against even moderately armored men. Whereas at 100 meters, all of our bows are potentially lethal, and some quite likely to defeat armor. Below that, lethality will rise rapidly, both as arrows arrive with the power to defeat more formidable defenses, but also as archers are close enough to their targets to begin aiming at weak points. Tactical implications for foot archers. Okay, the math is done. I promise. You can come out now. The key takeaway here is that against even mildly armored enemies, the lethality of arrows drops off over range. This isn't linear. The drop-off is much more extreme close to the maximum range of the bow or crossbow because of increasingly extreme increases in the angle of impact. But the arrows absolutely do not deal their full 53 damage, remembering our Total War example, out at maximum range. That has major tactical implications. Let's recap the ideal tactics that the Total War model produces. Ranged units begin firing immediately at their absolute maximum range. Moreover, they attempt to keep to this exact range, or just within it. Units that can fire while moving should move backwards, maintaining absolute maximum range at all times. Finally, maximum range is the single most important factor in ranged combat, as the ability to fire at full power while not receiving any return fire is incredibly valuable. In contrast, actual archers seem to have almost never fired at their maximum range. Mike Lodes, cited above, claims that there are no scenes of bowmen firing high arcs outside of siege context in the whole of medieval art. I certainly have not seen one. Of course, bowmen fire arrows upward in siege context, but the 45-degree maximum range arc doesn't appear in artwork featuring battlefield conditions. Now, at Agincourt, 1415, the initial English volleys do seem to have been at very long range, but following Keegan, The Face of Battle, 1976, Inter alia, these volleys weren't intended so much to cause damage as to goad the French into a foolish attack, a psychological impact. The actual killing the longbows did happened once the French began advancing. Image. Illustration of archers exchanging volleys. Image description. Early 15th century manuscript showing archers apparently exchanging fire at close range. One assumes that the artist has taken some liberties to fit the entire scene into its composition. End of image description. Moreover, we see quite clearly that the existence of the longbow, with its considerable reach, did not drive other missile weapons from the battlefield. Of course, the longbow was a socially embedded institution. The princes of Europe could not all just replace their own troops with longbowmen, even had they wanted to. Edward III is said to have quipped, quote, "If you want to train a longbowman, start with his grandfather," end quote. But I do not know the primary source attribution of the quote. But if the longbow had rendered crossbowmen next to useless, one assumes the French would stop using them. They did not. Despite the crossbow's lesser range, rate of fire, and only small advantage in penetration ability, we are speaking here specifically of battlefield crossbows, there are siege crossbows with much higher release energies. They did not, despite the crossbow's lesser range, rate of fire, and only small advantage in penetration ability. We are speaking here specifically of battlefield crossbows. There are siege crossbows with much higher release energies. So clearly, the crossbow was not made entirely useless by these factors. This exercise gives us our answer. Maximum range was not only not all important, it was almost unimportant. What mattered was effective range, a much fuzzier concept, incorporating not only how far the bow could throw an arrow, but the balance of the average armor of the enemy with the average power of the available bows. While the longbow could outperform a period crossbow, it did so at relatively low lethality. So the crossbowman, given the protection of some armor or a shield, might confidently expect to be able to walk the range distance and begin firing. This, of course, happened at Crécy. The French employed Genoese crossbowmen were able to reach range and begin, and lose, an archery duel with the English. Though it was probably quite short. There is some debate on this topic which I will not embark upon here, which the Genoese lost on account of not having been given the time to bring up their pavises, standing shields, for cover. In the Total War model, the crossbowmen would never have reached range in the first place. Compounding this concern is ammunition. In the Total War system, there is little need to save ammunition for the final high lethality approach, because shots have the same lethality at all distances. But firing endurance, both of the archer and his ammunition, was a real concern. A longbowman might very well spend all of his ammunition, or the strength of his arms, in just a few minutes. Wasting that window of fire on very ineffective long-range plinking would have been extremely foolish. Instead, the evidence strongly suggests that even English longbowmen held their fire until considerably closer distances. I do not know that anyone has nailed down the exact zone precisely. The evidence seems insufficient to support a whole lot of precision, but it seems to be somewhere around 80 to 100 meters. Loads suggest as short as 50 meters, but this seems excessively short, given the primary source descriptions and battlefield topography. This, in turn, neatly fits into the distance where arrow lethality against armor begins increasing rapidly as longbow arrows begin reliably penetrating mail. Remember that even for plate-armored knights, some vulnerable areas, like the armpits, neck, or groin, might still only have mail protection. Tactical implications for horse archers. The mobility of horse archers, by which I mean true steppe nomad style horse archers, not horse mobile foot archers of the English type, creates an even more complex set of tactical considerations. Moving foot archers around the battlefield can be quite difficult. It is generally agreed, for instance, that the English longbowmen at Agincourt were very vulnerable while they picked up their stakes and moved. The subsequent experiences of English archers being caught out of position in the late phases of the Hundred Years' War seems to confirm this. For example, Formigny, 1450. Such movements are also complicated from a command perspective, if they haven't been planned. Horse archers have much more mobility, and thus the ability to effectively dictate range. But the evidence suggests they did not plink at maximum range either. Timothy May, The Training of an Inner Asian Nomad Army, JMH 70, 2006, and The Mongol Art of War, 2007, 72-74, argues quite persuasively that the Mongols used the caracole to attack with bows. The caracole is to turn a horse about. In battle, this typically means riding up to an enemy at speed and turning around just short of him, while firing some kind of ranged weapon at close range before galloping away. What this would look like: an individual Mongol rider would charge in at speed from outside of effective bow range. We've already discussed how terrifying an onrushing horse can be, and this advantage, instead of sitting still at range, gives the onrushing Mongol the full morale advantage of that terror. He can fire as he moves forward into the enemy, putting a storm of arrows in the air, which will all seem to arrive almost at once because of his speed relative to them. But at about 50 meters of distance, instead of charging home, the rider wheels about and begins riding away at speed, firing backwards, the famous Parthian shot. In the turn itself, the rider is positioned to fire one point-blank range, highly accurate and deadly shot. Image. Diagram of the caracole maneuver. Image description. Diagram of a caracole maneuver following May 2007. The horse archers fire on the approach, but their lethality rises dramatically as they close in with the apex of the charge, before turning around. The Parthian shot technique allows them to also fire on the second half of the caracole. Multiple ranks perform the attack together, allowing for a continued barrage. End of image description. May argues, on the basis of what he sees as preserved steppe drills and Mamluk warfare, that the Mongols likely practiced this tactic extensively. The trick, beyond the tremendous skill required to be effective individually as a horse archer, was making it work with a whole large group of horsemen. Doing so requires all of the horses to move in time together and perform the caracole at a predictable distance so that multiple ranks, horses stacked behind each other, and files, horses to the left and right with a wide distance interval for the turn, could attack at the same time, one rank after another. The effect for infantry would have been terrifying. Instead of a moment of shock at the cavalry charge, the terror of onrushing horses might be maintained for minutes at a time with a continual barrage of arrows. The arrows would also pick up speed from the forward motion of the horse. And in all of that, the ever-present temptation would exist to either run out after the retreating horseman after his turn, with the Mongol riders behind him perfectly positioned to slaughter any man foolish enough to try it, or to run away from the danger, to be run down and slaughtered. Image: Japanese horse archer in drill. Image description: a Japanese horse archery drill. Video here. Note how close he is to the target. What is being practiced here is not long-distance archery, but accuracy at high speed at close range. Also, I too would be hiding behind an arrow-proof screen, like those people on the right. Horses are scary. End of image description. For our discussion, what is really crucial here is how this tactic interacts with range and penetration. With step composite bows rivaling the power of a longbow, at the apex of his approach, the step warrior is going to be hitting his shots with all of the power of a point-blank longbow shot, defeating mail and even potentially modest plate defenses. Lamellar armor was quite common in China, for instance. A high-power, close-range hit might rupture the connections between plates. For example, here. Those shots at the apex are also going to be very accurate. Steppe warriors trained in archery in part by hunting even small game on the steppe, and an archer who can hit a running rabbit on open ground reliably can also drop his arrows into the unprotected face or neck of a lightly armored infantryman with some frequency. The lethality of this sort of archery would be much higher than the sit and plink style of total war tactics. But it also posed real risks. The turn of the caracole is executed dangerously close to the enemy, such that a well-timed countercharge with cavalry might catch the caracole as it turned. This might explain how heavier and less maneuverable cavalry sometimes manages to catch and defeat forces of horse archers which should, at least in theory, be more mobile. They don't need to charge the entire roughly 200-meter distance of bowshot, but merely time a charge over the last 50 meters or so to hit the steppe nomad as he reaches the apex of his caracole. This seems to be what happened at Nicaea, 1097. Two efforts made by Turkish horse archers under the command of Khalij Arslan to assault the First Crusade in siege around Nicaea were turned back quite roughly with significant losses after getting caught in close combat with heavier Crusader forces. Likewise, at Ain Jalut, 1260, the Mamluks were able to pull a Mongol army onto bad ground and catch them with the heavier Mamluk cavalry. Of course, such efforts to catch horse archers could be very risky. Publius Licinius Crassus was killed at Carrhae, attempting what seems to have been such a maneuver. Plutarch, Life of Crassus, 25. The Parthians expertly lure him out and then turn and destroy his cavalry and supporting infantry. Interestingly, Plutarch's description of the Parthian cavalry riding around them, quote, tearing up the ground and bringing up earth from the deep, end quote, such that the Romans could neither see nor speak, implies the sort of extreme close-range horse archery consistent with May's assumptions about Mongols above. The Parthians do this while raining shots into the Roman infantry until it collapses. The Parthians are not showering the Romans with arrows from afar, but riding fast and so close that the Romans are in their dust cloud, even in a dense infantry formation. It's also important to remember that in performing this kind of maneuver, even steppe horsemen are not the flawless automatons of video games. In video games, players can view the battlefield from above and instantly give orders, which their units, again, execute nearly instantly. For steppe horsemen surprised by a countercharge or a deluge of unexpected foot archer fire, an effective and unit-wide reaction would be far more difficult to pull off. Conclusions. So, to recap, the lethality of archery was highly dependent on distance against even moderately armored enemies. As a result, arrow fire had to be delivered well within the maximum range of bows in order to be reasonably effective. For horse archers in particular, this entailed moving much closer to enemies in order to deliver devastating close-range fire in a caracole maneuver before withdrawing, often repeatedly. This is, of course, a very different tactical environment than the maximum range archery exchanges modeled in most computer war games. I've picked on the Total War series, which, to be clear, I quite enjoy, but all sorts of titles, Mount and Blade, Chivalry, Age of Empires, etc., indulge in this. Why does it matter? I think there are three main points where having this mistaken mental model of how archery works can lead students of historical battles into error. The first error is the immortal horse archer. In many of these games, it really is nearly impossible to defeat horse archers with anything but other horse archers. Now, I don't want to overstretch this point. Man for man, horse archers were probably the most skilled and fearsome individual warriors on an ancient or medieval battlefield. But they were not immortal. It was possible for light or even heavy cavalry to catch these horsemen, although doing so required uncommon command skill or at least forced errors by the horse archers. Those steppe horsemen also had to come well within the effective range of other ranged weapons, like crossbows, heavily used in China for this purpose, and even some throwing weapons, to be effective themselves. Han infantry tactics combining pole weapons, ji, with crossbow troops suddenly make a lot of sense in this context. An infantry formation that can project deadly ranged fire is actually a tough nut to crack for even a steppe nomad, which is why steppe nomads often simply avoided large agrarian armies, letting the logistic nightmare of steppe operations do their work for them. I sometimes wonder if the lionization of the warrior, rendered seemingly untouchable by his superior weapons system, in turn influences how we perceive the effectiveness, or lack thereof, of our own highly mobile, seemingly untouchable missile troops of the sky. If we think that standoff weapon systems worked this way in the past, but as I hope I've shown, they didn't, we might expect them to work that way in the present. In reality, the morale shock of pounding hoofs did much of the work of the steppe horse archer, a tool that the modern fighter bomber mostly lacks. For example, sirens on German Stukas. The second is the unwise assumption of the supremacy of the technological over the psychological. The maximum range vision of archery encourages students of battle to focus on just that, the maximum range of the bow, making the battle entirely about the weapon and its technological characteristics. But the battles more often turn on what's in the archer's heads than what is in his hands. To be effective, the English longbowman must keep his wits and his position and continue firing even as the pounding hoofs of the French knight are only 100, then 75, then 50, then only 25 meters away. The striking power of the longbow may be necessary to make this tactic work, but it is not sufficient. The key element is not the bow, but the cohesion that holds the men together. Likewise, the steppe composite bow is a fearsome weapon, but what makes it work so well is the psychological strain that the continuous, terrifying assault puts on the agrarian enemy. To stand under fire is extremely difficult. To stand in the face of fire and continuing cavalry charge demands extreme discipline and cohesion that fairly few troops could muster. It's important to remember that winning a battle lies in making the enemy run away. In too many games, the power of the steppe horse archer is their ability to kill the enemy, rather than their ability to rout the enemy and then ride them down. Finally, this sort of analysis helps to explain why gunpowder weaponry was viewed as desirable, especially against armored infantry, particularly in Europe, even though it was less accurate and slower firing than bows. This question is a frequent one from students in light of the low rate of fire and poor accuracy of early arquebuses. By the 15th century, guns were already delivering much higher impact energies, 500 to 1000 joules. By the 16th century, this was 1300 to 1700 joules than any bow, and while a bullet requires, because of its shape, more energy to penetrate, even then the lethality of firearms quickly eclipsed bows, especially against armored targets. Given a choice between 5 shots, which might wound a target, and 1 shot, which would definitely disable him, it's not hard to see why the preference for the latter developed. Well, I think it's time for bows to bow out for now. Next week, agriculture and what the countryside around a pre-modern city should look like. Hint, it won't be empty. Image: the landscape around Highgarden from Game of Thrones. Image description: as you can clearly see, the wealth of Highgarden was in agriculture. I mean, just look at all the farms. Perhaps they raised sheep. It would explain why all of the grass is so neatly mowed. End of image description. This has been a recording from a collection of Unmitigated Pedantry, the blog of history professor Bret Devereaux, recorded by myself, a great divorce, for accessibility and sharing purposes. If you enjoyed this content and wish to engage with it or support Bret, please check the description for links to the original post on his blog, his Twitter, and his Patreon. I highly encourage you to share, support, and engage with his works on any and all platforms, if you are so inclined. If you wish to support me, please do remember to like, share, and subscribe to this or any other content here that you enjoy. Thank you so much for listening.